Alright, guys. So, in one of the emails earlier this week, I told the class that I'm going to um, review the exam and um, possibly do a video for you for the most mistaken problems on the exam. And here's that video. Alright, so I was looking at my exam statistics and kind of surprised me a little bit that the most mistaken problem on this exam is, ta-da, this question about two scientific notation number subtracting each other. Okay, so I don't know. Looking at the percentage, I only have about less than 20% of the students getting this one right. This is one of the 2 to 3 questions that has a correct rate less than 50%. And this one is by far the bottom one. No. And all right, so here let's solve this question first. I can understand why you would choose that wrong answer, which is this guy. Okay, but let's do it the way that we talked about in our video lecture. Okay, so when you're subtracting two exponential numbers, of course, you always need to turn them into the same power. Okay, without the same power, you can't add or subtract them. All right, so let's do that. And it doesn't matter which one you turn to match the other. Okay, so all right, I'm going to use 1.56. I'm going to keep the 10 to the 15ths. Okay, and I'm going to subtract. And now I'm going to turn this guy into 10 to the 15th power. And that means add 1 onto the power of 10. And that means move the decimal 1 spot to the left. So 0.801 times 10 to the 15th. So now you can do this subtraction. And the deal here is that you're subtracting these two numbers. And subtraction, we follows what? We follow what? Decimal place. That's 2 decimal place. That's 3 decimal place. So although your calculator, after you punch this number in there, tells you you get 0.759 times 10 to the 15th, okay, you gotta know that you should only have 2 decimal places. Whichever component of your addition subtraction with the least number of decimal places will determine the number of decimal places in your final result. And this is your final result. So you have to round up your 9 and turn it into 0.76 times 10 to the 15th to keep your 2 decimal places. And of course, we also ask your final answer in scientific notation, and 0.76 times 10 to the 15th is definitely not scientific notation because 0.76 is less than 1. So you're going to have to move it 1 place and then subtract 1 from your 10 power, and that's going to give you the correct answer, 7.6 times 10 to the 14th. Okay, so this is not scientific notation, that can be excluded. This is not scientific notation, that can be excluded. This one, I don't think anybody is choosing this one. It's completely out of range. Okay, vast majority of the answers are focusing on these two, and unfortunately, this one was chosen by about 80% of the students, and doesn't mean it's right. Okay, and I can understand the confusion. Well, you have 3 sig figs there, 3 sig figs there, and well, this one has 3 sig figs. That's 2 sig figs. But you're doing subtraction. do we really care that much about subtraction when we are care that much about sig figs when we're doing subtraction? And of course, the other, I know you would be saying, well, that's 2 decimal place, that's 2 decimal place. Okay, now in a normal subtraction, okay, if you can subtract the 2 numbers directly, then yes, your final answer, you should keep 2 decimal place. Okay, but you can't. This is an exponential number subtraction, which we talked about that you have to turn them into the same 10 power. And when you turn them into the same 10 power, your number of decimal place of the numbers are going to change. And the reason we ended up with 0.76 is actually we are following the rule of keeping 2 decimal place. Because if you get 759, that's 3 decimal place. And this doesn't change even if you want to do like 10 to the 14th. Well, let's do it that way. Okay, so if you say, well, I'm turning both of them into 10 to the 14th, well, that means the first one is going to need to change, and I subtract 1 on the power, and that means decimal place move to the right. Okay, and that's going to give me 15.6 times 10 to the 14th minus 8.01 times 10 to the 14th. Okay, so how many decimal places you have now? That's 1 decimal, that's 2 decimal. Your result, although it's 7.59 times 10 to the 14th, your result is limited by 1 decimal. So you have to round it up to 7.6 times 10 to the 14th as well. So either way, the correct answer for this question is 7.6 times 10 to the 14th power. All right, so it's a little surprising, but on the other hand, no, I can understand where the mistake is coming from, like how hidden the mistake of this problem could be. Okay, and you have to really know your rules, and to be able to figure this one out. Yeah. And now, is actually this guy. Yeah. Which one of the following is a correct formula of an ionic compound? Okay, so vast majority of people were able to eliminate 3 answers: B, C, and D. Okay, so Na is +1, sulfur is -2. There's no way that these two can match up 1-on-1, so the correct one would be Na2S. Okay, ammonium is +1, sulfite is -2, so correct formula would be NH4. You would need 2 of that to offset the -2 charge on sulfite. Strontium is in group 2, so that's +2 charge. Iodine is in group 7A, and that's -1 charge. That's the fluorine-chlorine group. So the correct formula of these two should be SRI2. No. And majority of the wrong answers came on this particular formula. Okay, and if you put the charge in, now this actually works because magnesium is in group 2 and chlorine is in group 7A, and +2, -2, okay, 2 of those would be +4, 4 of those would be -4, so charge does cancel. But one thing we did emphasize on ionic compound formula is that, and if you go back to on your video lecture, you should see that. If you go back on the notes you're taking for the video lecture, you should be seeing that as well. Okay, now, for ionic compound, it's the smallest whole number ratio for your subscripts. Okay, because ionic compounds are making 3-dimensional arrays, Okay, they're not making molecules. You don't really have two of these ions, magnesium ions, together with four chloride ions and make an individual little group of this compound. That's how molecular compounds do things. Ionic compound did it in a way it's all about the ratio. Okay, and in this case, 2 to 4 is definitely not the smallest whole number ratio for the two, for the cation and the anion. What should be the smallest whole number ratio? Obviously 1 to 2. And that's why magnesium chloride would have the formula of MgCl2. All right? This one, although it kind of looks weird, I've never dealt with this compound before, but we do know that if you search the element on your periodic table, gallium is right underneath aluminum. So this is group 3A. Okay, the common metal charge for group 3, if you go back looking at your notes or our video lecture, is +3, just like aluminum. Okay, and then you see nitrogen. Nitrogen is in group 5A. Non-metals make negative charge, the typical negative charge on nitrogen or phosphorus, okay, or arsenic, okay, should be -3 charge. 1-on-1 ratio, 1 gallium, 1 nitrogen. That's a correct ionic compound formula. Smallest whole number ratio, correct charge. All right, so this is the number one mistaken conceptual problem. Now, the next one on the list is the limiting reagent problem. Okay, so let's go to the next one in the line. Oh, shoot. Is this question about conversion. Okay, somehow this one also got more than 50% of the students. And well, let's see how we set this up. Okay, so this is a conversion problem, so 75.0 centimeter squares per second. Okay, I want feet square on top and a minute on the bottom. So it's just lining up your conversion factors, so this could cancel. All right, I don't need centimeters, so I'm going to take care of a centimeter first. 2.54 centimeter is 1 inch. Okay, now, yes, you could cancel, okay, this here. But what you cancel is 1 centimeter. You're not canceling both centimeters. Okay, so you would need another 2.54 centimeter, 1 inch, to cancel the other centimeter. And now you got inch square, but inch square is not what you want. But we also know that 12 inch is 1 foot. So that cancels 1. 12 inch, 1 foot, cancels 2. So now you got foot square on top. And then the last one, of course, it's 60 seconds. It goes to 1 minute. Okay, so second cancel. Now you got foot square over minute. Okay, so your result should be 75 times 1111 times 60 divide by 2.54 times 2 square, and then divide by 12 square. So punch that into your calculator. I'm going to do it again on my calculator. 75.0 times 60, and that's give me 4,500. Divide by 2.54, 1,771. Divide by 2.54. That's 697.5. divide by 12, 58.1, divide by 12 again, 4.8437, doesn't matter. Correct answer, B. Okay, 4.84, because that's keeping your 3-sec fix. All right, so that's the number 2 on the list, most mistaken problems. The next one, reagent problem. The one after that should be the percent yield problem, which is right here. Okay, so let's read the question. How many grams of ammonia will be produced? So I want to know the amount of this guy when 100 grams of nitrogen gas, so 199 grams of this guy, reacted in this reaction, okay, at 75% yield. And we have an unbalanced equation. So first thing first, you want to do stoichiometry, and percent yield is a stoichiometry problem. You want to do stoichiometry, you better balance your equation. Now, the equation itself should be pretty easy to balance. Okay, you're going to need at least two of those, because you got N2, that's 2 nitrogen, each ammonia only have 1. And then if you're going to get 2 of those, that's 6 of hydrogen, so you better have 3 H2 molecules. And you don't need anything for N2, so that's a balanced equation already. Okay, now 199 grams of this, of reactant. No, and of course you have a percent yield here. Now, what do I do with this 199 grams? Can I use the 199 grams to do stoichiometry? Remember, what is N2? N2 is a reactant. Okay? Yield. Does yield have... Did you calculate the percent yield with reactant? No. Percent yield is theoretical yield, theoretically how much product you can get, and actual under actual yield how much product you get. Both of them are products. Okay, so use your reactant to do direct calculation. 199 grams of N2. Okay, so each 1 mole of N2 is 28.02 grams, and then each 1 mole of N2 produce 2 mole of NH3, and then each 1 mole of NH3 is 17.03 grams. Okay, so grams cancel, mole of nitrogen cancel, mole of ammonia cancel. So 199 divided by 28.02 times 2 times 17.03, and that's 241.9 grams of ammonia. Okay, now you got a yield. What is this yield? This yield you calculated from stoichiometry. Stoichiometry means what? If every molecule within the 199 grams of nitrogen, okay, is turning into ammonia, then you're going to get 241.9 grams of ammonia. But is every single molecule of nitrogen turning into ammonia? Well, obviously it's not. 75% yield means, or 25%, a fourth of your reactants are actually lost along the way. Okay, so this is how much product you can get on paper when every molecule changes. On paper, that means theoretical yield. So whatever your actual yield is over the theoretical yield times 100% should equal to the 75.0%. Okay, rearrange the equation. Your x should equal to 241.9 times 75%. Okay, and that's going to give you 181 grams actual yield. So how many grams of ammonia you actually going to produce? Answer D, 181 grams. Yeah. All right, so the next one on the line is, where is it? Okay, so aniline. Okay, so here it is. All right, you have 25 grams of aniline, so 25 grams of this guy, and you have 106 grams of bromine. And you want to know which reagent is in excess and how much of it is left over. Okay, so we already know how to deal with limiting reagent problems. You have to calculate from both of your reactants to the same product, okay, and to see which one gave you the smaller number, a smaller production of the product. And that one is your limiting reagent, and then the other one must be your reagent in excess. All right, so 25 grams of C6H7N times 93.13 grams per 1 mole of this guy. Okay, and each 1 mole of C6H7N is going to produce me 1 mole of C6H4 MbR3. Okay, and you could continue with the molar mass of this and get grams. Okay, but you could also, since we're not looking for how much of the product is made, okay, you could also stop here at the moles, whichever one give me the smaller amount. Amount could be in moles, amount could be in grams. Okay, that makes no difference. So if you want to save one step in your calculation, you can do that in this case. So mole of this cancel, gram cancel, I get moles of that. So 25 divided by 93.13, and then the rest of them are all ones, so 0.268 mole of product C6H4NbR3. All right, so then the other one, let me make this a little bigger. (106 grams of Br2, 159.8 grams Br2 per 1 mole Br2. Each 3 moles of Br2 produces 1 mole of C6H4NbR3. Mole cancel, grams cancel, give me mole. So 106 divided by 159.8 times, divide by 3 again. So 0.221 grams. Sorry, not grams, moles of the compound. All right, Now the comparison should be obvious. This is the smaller one, so this is the limiting reagent. So despite the fact that you have more bromine, bromine is your limiting reagent. Okay, so this guy would be your reactant in excess. So once you determine that, only possibility of the correct answer is A and B. Okay, so how much of C6H7N is aniline is left? Well, let's figure out how much aniline we used. We can use the grams of bromine, the limiting reagent, turn it into moles. Each 3 moles of Br2 react with 1 mole of C6H7N, and each 1 mole of C6H7N is 93.13 grams. So grams cancel, mole cancel, mole cancel, give me grams of C6H7N used, and that is 20.6 grams of C6H7N used. Well, you had 25 grams, you used, so 25.0 grams obviously. Now, you used 20.6 grams, so 25.0 minus 20.6, 4.4 grams left. And A is the correct answer. Okay, so that's the limiting reagent problem. That's the next one on the list. And all right, so let's get there. And the next one on the line is the average atomic mass problem. So let's go there. I remember seeing it somewhere. Okay, all right, so there we go. Potassium has 2 stable isotopes, potassium-39 and potassium-41. Okay, each have atomic mass of close to 39, atomic mass close to 41, and if the average atomic mass is 39.10 atomic mass unit, what is the natural abundance of the heavier isotope of K41? Well, first of all, before we do anything, okay, now let's look at these 3 numbers. That's 38.9, almost 39, 40.9, okay, 96, that's almost 41. And the average is right here in a little bit beyond 39. So which one of the isotopes is closer to the average atomic mass? These 2 numbers are only about 0.1 something away. These 2 are actually 1.8 something away. Okay, the difference between these 2 is about 5% of the difference between the average atomic mass and this heavier isotope. Closer to that means what? This guy is taking the more weight in the weighted average. So there's more K39 than K41. And right there, that eliminates 2 answers for you. These 2 can't be possible. Okay, now, what else can I do? You're asking, how do I set up this calculation? Natural abundance of K41, let's say that's X. Okay, well, if that's X, what's the natural abundance of K39? Now, you don't need to set it up as Y, okay? You don't need 2 unknowns to calculate. But you only have these two stable isotopes. One of them is X, okay? What is the other one? 100% minus X, okay? Or what is 100%? 1. So 1 minus X. All right, so your setup then should be simple. 38.9637 times 1 minus X plus 40.9618 times X should equal to 39.10. Okay, so extend your equation. 38.9637 minus 38.9637 X plus 40.9618 X equal to 39.10. So on this side, group these two together. So 40.9618 minus 38.96837. So 40.9618 minus 40.9618 minus 38.9637. So 1.9981x should equal to 39.1 minus 38.9637. 1363. X should equal to 0.0682 and 6.82%. That is your correct answer. Okay, and these are the top 1, 2, 3, 4, 5, 6 of the most mistaken problem on this exam 1. The rest of them, the rest of the questions, the correct rate is all above 60%, which means more than 60% people getting them right. So it's not an overwhelming problem. Okay, and I'll let you review them and find the answers. And if you have problem solving one of them, let me know, okay? And make sure you review your mistakes, okay? This is about the most effective way to improve yourself in this class. Find your mistakes, correct them, find out how did you make those mistakes, what is causing you, okay, those mistakes. How does it relate to the way that you study, that you prepare for the exam? Now, what bad study habit some of these mistakes may indicate? Okay, you have to do a really, really careful analysis about your mistakes in the exam to prevent them from happening again. And hopefully this video can help a little bit, because these 6 questions that we talked about here are the most mistaken problems on this exam.